Right, time to move. A somewhat more interesting topic today because it's closer to your practical applications. That is the first stage in any electronic structure theory calculations. Essentially, before you do anything consequential on the molecule, you need to know what your molecule is. And typically, you would only have some approximate guess, like, well, okay, roughly the atoms are here and there. But what you need to first find out is the configuration of those atoms that gives you the minimum energy. And that would correspond to, more or less plus or minus at notionally 0 Kelvin temperature, the geometry that the molecule is going to have within the medium that you put it in. And then the question is, how do we obtain those equilibrium geometries? And this is what today's lecture is about. Okay, so firstly, the choice of coordinates. We can simply specify Cartesian coordinates for every atom. So for example, for methane in angstroms, and I would remind you that 1 angstrom is the length of a CH bond, quite convenient in chemistry. This is what we would have. We would put the carbon at the origin. The first hydrogens 1 angstrom away on the z-axis, and the remaining 3 are 1 angstrom away in the other 3 principal directions of the tetrahedron here. However, that turns out in practice not to be the best possible choice, at least not a terribly natural choice, because imagine if you have some giant protein with many chemical bonds and many interacting atoms. If you move one atom, that generally requires a rearrangement of all the other atoms around it to accommodate the new placement of the atom you have. So Cartesian coordinates would interact with each other, and then the optimization might take a long time because every atom influences every other atom in, well, a small enough molecule, it would. But then there are some natural coordinates like a bond length, and changing the length of a bond by displacing entire functional groups might actually be a better idea. And so early on chemists have decided to use something they call the Z-matrix, and that is a list of coordinates that is more natural for chemistry. You would have the same list of atom labels in here. However, then you say, okay, carbon sitting at the origin. Then hydrogen connected to atom 1, which is carbon, and the bond length is this. Then the next hydrogen connected to atom 1, and the bond length is this. However, with respect to the atom 2, which is the previous hydrogen, it makes an angle between the bonds of 109 degrees. Then the next hydrogen is connected to atom 1, and that's the bond length, and that's the angle that the two bonds of this one and of atom 2 make, and that is the dihedral angle, and this is a schematic, so that's your bond length, that's your bond angle, and that's the dihedral angle, so between the direction of this vector and that vector. And that's a 120 degrees. And likewise for the third proton. And in some cases, you would have an extra type of coordinates called out-of-plane bends. They are actually dihedral angles, just slightly unobviously arranged in this case. So this, because this is chemically natural, turning a bond or stretching a bond or twisting a dihedral still causes a rearrangement of the nearby geometry, but it is significantly smaller and more natural for chemical systems. And so the displacement tend to be significantly less interdependent than they had been in Cartesian coordinates. And so the process of geometry optimization converges in fewer iterations if you use Z-matrices. Then, of course, in principle, you can make your own parameterization. Whatever your molecule is, you have n atoms, and therefore 3n minus 6 independent coordinates in here. Remember, 3 overall translations and 3 overall rotations do not matter, so you have to subtract the 6 coordinates out. So 3n minus 6 independent coordinates. But you can parameterize it in various fancy ways, including with some nonlinear functions. And so that is in general called internal coordinates. So a coordinate system that you may have designed that is natural in some way for the molecule in question. So the simplest possible choice is Cartesians. The slightly more sophisticated choice that is still possible to do it automatically. In fact, Gaussian does it automatically. It runs optimizations in Z-matrices, unless you insist on Cartesians. And then if you really do insist, and if you've got some, for example, specified reaction coordinate, and you would want to parameterize with respect to some coordinate of some chemical reaction, then you may want to design your own specialized internal coordinates there and do the optimization with respect to those coordinates. Sometimes Z-matrix might not be a good idea, and this is an example of a molecule from, in fact, a paper I had published 20 years ago, where changing a bond length is actually a bad idea. Imagine if we change, say, the angle, right, between here and here, or some bond lengths there. What is going to happen is that this entire molecule will bend. And even though the change in the angle here might be slight, the displacement of the atoms here could be giant. And that's a bad idea because you might just land into atom collisions, even for tiny steps with respect to your geometry. So for very extended molecules, Cartesian coordinates might actually be better, because at least if you are displacing individual atoms here, you run no risk of atomic collisions. And therefore, your energy is not going to blow up and your optimization is not going to throw an error in the end. So choose carefully for very small molecules, Z-matrices, for intermediate molecules, either Cartesians or internals, and for large molecules, more or less, you will not encounter them because any realistic quantum chemistry method would, just crash your computer in there. So Gauss view can do user-friendly translations, at least between Cartesians and Z-matrices. And Gaussian itself, if you read the manual, has a really sophisticated interface that can do nearly arbitrary internal coordinates in there. Okay, so once we've got our coordinates, what would we do with them? Well, we would adjust them until the energy is minimized. And within the Born-Oppenheimer approximation, so atoms moving a lot slower than electrons, essentially the energy depends parametrically on the coordinates of all the nuclei. And so at each particular nuclear set of positions, we run the electronic structure, we obtain the total electronic structure energy, we move the atoms until we have obtained the energy minimum, and then this is our equilibrium geometry. And the process of finding the coordinates that minimize the energy is called geometry optimization. And in most calculations, that would be the first thing that you're doing, because otherwise, really, your energy is not in the minimum, and you don't really know what you are computing in that case. So what is a minimum? Well, a minimum is a stationary point on some surface, energy surface dependent on the coordinates. And this could be very high dimensional, right? If you have 50 atoms in your molecule, you are going to have 150 coordinates minus 644 independent coordinates. So this would be a 144 dimensional optimization. Quite a complicated thing, as you can imagine. And then we are looking for a minimum like here, and the minimum, as you know from your basic calculus, means the zero gradient. And the gradient is a derivative of the energy with respect to atom displacements. And so we need to calculate at the very least first derivatives of the energy with respect to these displacements. And on occasion, we may want the second derivatives as well. And well, if this gradient is zero, then we are in a stationary point. However, a stationary point could be a minimum, could be a maximum, could be a saddle point like here. And so in order to diagnose it further, we need the matrix of second derivatives, which is the curvatures. And if all curvatures are positive, so all Hessian eigenvalues are positive, we are in a minimum. If all are negative, we are in a maximum, but that's very uncommon. In a lot of cases, however, you would have an indefinite Hessian, meaning the eigenvalues of both signs. That means a saddle point. And if you are looking specifically for some transition states, maybe that's what you want. But in a lot of cases, that's not what you want. And so at the end of all optimizations, it is a good idea to compute the Hessian, check its eigenvalues to make sure you are in fact sitting in a minimum. All right, so how would we find that minimum? There are various methods, and I would go from the worst to the best. The worst, absolute, desperate method when derivatives are not available to begin with, that is exceedingly rare, but sometimes happens. For example, if you are measuring something experimentally, right? Instruments would have noise, noise is not differentiable, and so you cannot have analytical derivatives for some reason. In that case, what we do is use a method called Nelder-Mead simplex. And simplex is the smallest convex polygon in a space of a given dimension. In 2 dimensions, it would be a triangle. And then what we do is we pick this set of coordinates, that set of coordinates, and that set of coordinates. We compute 3 energies. We find the largest one, and we reflect the corresponding point in the centroid of all the other points. So it would go poof here. Then we recalculate the energy here. We pick the largest energy, and for example here, and we reflect it in the centroid of the rest of them. Poof, we'll end up here. And likewise there, and so on. And also what can happen here, if this is not the new lowest energy point, in some circumstances, the algorithm can shrink this simplex. In some cases, it can expand it, so it can adapt its size to the local curvature and the local circumstances. And step after step after step, eventually this thing converges into a minimum. Now, the good thing about it, it doesn't actually need a gradient. It is very cheap, because gradient, well, it's a derivative of the energy with respect to a lot of different parameters and can be expensive to compute. It works for discontinuous, noisy, and even multi-valued irreproducible functions. Right? For instruments particularly, this is really quite useful and broadly deployed, and it can also sometimes jump out of a local minimum. However, this method is very slow. It needs, multiple steps to reorient itself, to shrink itself, or expand itself, or expand and move and shrink. Thousands of iterations. Even for tiny molecules, it can go for a long, long time before it converges. Easily gets stuck, and there is no mathematical guarantee of convergence. So this is virtually never used in electronic structure theory, but is used a lot in experimental work. The simplest thing that is used in electronic structure theory, or perhaps was the state of the art in the 1960s, is the gradient descent. What we do is we take our function, energy in our case, we calculate its gradient. You know that the gradient is the direction of the steepest growth, but we want to minimize, so we just step in the opposite direction. So we put a minus in here. And k is the step length. And occasionally we can also try a few points in the descent direction and pick up the best possible k. This is called line search in the descent direction in there. And so k is the minimum along the particular multidimensional direction. Okay, that works a lot faster than simplex, but it still has its own problems. Even the simplest energy surfaces, like this biquadratic surface, so ellipsoidal minimum, you can see it's sort of zigzagging. If you step down the gradient every time, you would have this zigzag. And then the smaller the gradient, naively, the smaller the step, and so it does converge slow. So convergence is guaranteed to the nearest local minimum, easy to implement, easy to understand, relatively inexpensive. You only need first derivatives in here, but slows down as you are approaching your minimum, not applicable to noisy functions like, for example, this beast, right? Gradient descent will just stuck immediately in a local minimum on such a surface. And, well, the perennial problem of all convex optimizers, it converges to the nearest local minimum. Whether or not it's a global minimum, you have no way of telling. And this is where your chemical intuition comes, right? Chemists are pretty skilled at guessing what your molecule is going to look like. And so starting from a good initial geometry does guarantee that you converge to a sensible equilibrium geometry. And if you start from some horrible nonsense, then it will converge to another horrible nonsense that just happens to be some metastable intermediate. So be careful where you start. You will converge to the nearest local minimum to that point. Right, so gradient descent. There are somewhat better versions of that, and they are different in that they recognize that not only do you have the gradient at this particular current point you are sitting in, you also have the history of all the previous gradients. And the history of first derivatives on a trajectory can allow you to at least estimate higher derivatives and maybe choose a better direction of your next step based on the local curvature information that you might infer from them. So the simplest implementation of that is called conjugate gradients, where you take a step along some direction, but that step is not just the gradient, it's the current gradient plus a little bit of the previous direction of the steps that you took. So it has a certain amount of inertia. And if you've done machine learning a little bit, you will remember that a lot of the stochastic gradient descent optimizers like Adam, they do have this inertia as well. This is why Adam has never been published in academic literature, only on arXiv. This is because, serious people in optimization theory looked at it, laughed, and said, well, this is nothing new. Right, this was known in the 60s. So conjugate gradients use history of past gradients to decide slightly better descent direction. And that improves things if you do, for example, this optimization on a surface that is not purely quadratic but has higher order curvature. Gradient descent will take 60 evaluations if you start here until it arrives into your minimum to a certain tolerance. Conjugate gradients will take 3 times fewer evaluations, and that is a big deal if the calculation of your energy and then the gradient is expensive, like it would be in a high level method with a large molecule and a large basis set. So conjugate gradients does not exhibit the zigzagging that gradient descent has. So gradient descent here is in green, conjugate gradients is in red, so significantly faster. It is used a lot in numerical linear algebra for solving systems of equations, for inverting things. You may remember conjugate gradient type linear solvers in MATLAB. So they're super useful. So this is an improvement, and it does cut down the number of iterations essentially for free, because you have your history of the gradients you can simply store for free in the computer memory. But still, this is perhaps 1980s kind of level. What people realized somewhat later is, okay, we do know the history of the gradients. It does allow us to reconstruct somewhat the second derivatives. So why don't we try recognizing and reconstructing them a bit more precisely? And to do that, we first need to take a look at why would we need second derivatives in these optimizers. And this goes back to Isaac Newton in 17th century. So if we take our Taylor series for the function that we seek to minimize, what we will see is, okay, that's f of x, that's the first term in the Taylor series, so all the first derivatives, that's the second term in multivariate Taylor series, so all the second derivatives in this matrix and 2 vectors of displacements. And then we say, okay, if we take our gradient of this, so we differentiate this again, we get that and that. And then if we say that we want the gradient at the destination to be 0, so for that to be a minimum, then we put this to 0, we solve this for delta x, and this is our step. So you can see it's the vector of first derivatives times the inverse of the matrix of the second derivatives, the Hessian matrix. And this would have been based not on the linear approximations like gradient descent, but on the quadratic approximation, so much better approximation. And this converges really quickly. Remember, gradient descent took 63 evaluations on our surface here. Newton-Raphson converges to the same precision in just 6, so 10 times faster. The trouble, however, is the matrix of second derivatives is super expensive. If you have the same molecule with 50 atoms, 144 coordinates, so your Hessian is going to be 144 by 144, right? So over 10,000 elements, so over 10,000 derivatives to compute. This is really, really expensive. So even though the optimizer would take fewer steps in here, each step would be wildly more expensive. So, okay, for Newton-Raphson, very fast convergence, like here, well adapted for molecular geometry optimization. Remember, the energy dependence on bond stretch, for example, is approximately quadratic, right? Hooke's spring. The bonding energy change when you bend a bond is also roughly quadratic with the angle. The energy change with respect to the dihedral angles is cosine squared, for which a quadratic function is locally also an excellent approximation. And so Newton-Raphson molecular geometry optimizations converge really well, really quickly. And it's a bloody shame that the Hessians are so expensive. So why don't we try and reconstruct not just some adjustment to descent direction, but the entire Hessian from the previous history of the gradients? And a lot of thought has been put into that in the 1980s literature. Turns out you can, and the approximation gets better and better the more gradients you have. The Hessian is still somewhat approximate, but it's pretty good. And the equations involved in updating the Hessian are horribly complicated. I will not derive them for you. But if you know the Hessian at the previous step, and you can literally just start with a unit matrix, and you know the gradients and displacements from the previous steps, you can run this arithmetic here repeatedly and get a better and better approximation to the Hessian at the point you're currently sitting at. This BFGS update, Broyden-Fletcher-Goldfarb-Shannon, is particularly good. This is what is used in virtually every electronic structure theory package these days. So what Gaussian 16 would use when you start optimizing molecular geometry is a somewhat refined version of BFGS. You can refine it further to solve not just for the Hessian, but directly for the Hessian inverse. So it saves you a matrix inversion, which is also quite useful. And it can avoid all sorts of complicated mathematics in the middle of it, because this can be pretty high dimensional as well. So if you've got like a million dimensional optimizer, there's a special low memory version of BFGS, which never stores any matrices explicitly here. So this method is super sophisticated and super good. Read up on it if you have time, because in any kind of quantum technology that involves any kind of optimization, you will sooner or later come across either the Newton or the quasi-Newton, and more likely than not, specifically LBFGS. So it's wildly less expensive because you only need first derivatives, you're not computing the second derivatives, but only a factor of 2 slower than the full Newton-Raphson. It's asymptotically quadratic, so it's still better than conjugate gradients, as you can see. And in a lot of cases, the initial estimate for this Hessian here, the one you start updating, may be computed using very cheap methods if you are running your geometry optimization with, I don't know, configuration interaction. There's no chance in hell you would get a Hessian for that. However, you can run Hessian with some really cheap semi-empirics and then use that Hessian as the initial guess here, and that saves an awful lot of time in practical calculations. Okay, now, there is one little caveat here. Notice that you need to invert this Hessian, and not every matrix is invertible. If the matrix has a 0 eigenvalue, it is not invertible to begin with. It will blow out into infinity. Or if it accidentally has a tiny eigenvalue, the corresponding inverse eigenvalue will be huge. When you multiply it into the gradient direction, it will blow that direction out, and you will take an unphysically long step somewhere into a geometry that makes absolutely no sense. And so there has to be some kind of common sense limit that, okay, if my quasi-Newton method requires me to displace an atom by 5 angstroms, well, that's probably not a good idea, because it will throw the atom out of the molecule. If it wants to displace it by half an angstrom, well, that's still a pretty bad idea because it's going to break my bond. And probably I don't want that to happen. And so a sensible displacement for a molecule is maybe 0.1 angstrom per step. And so how do we ensure that that happens? Well, of course, we could put simply just a limit, right? This is called a trust radius. And Gaussian has it that any unreasonably long displacements are literally just truncated. So at the cost of slowing down the optimization, it guarantees that you're not breaking your molecule. However, a healthier way of doing that would be to eliminate small eigenvalues from Hessian to begin with. And since it's an approximation anyway, we might just as well add a little bit of unit matrix to it. That doesn't change things an awful lot, but it can move eigenvalues away from 0. And so the simplest thing here is to just regularize it like that. So trust radius. To have it imposed. That is still, well, it slows optimizations down because you are artificially clipping the steps. So this trust region method, Gaussian does use it if you insist, but a better method exists now, and that is to restrict your step by not using a Taylor approximation, which only uses power series, but to use something called Padet approximation, which is roughly just a ratio of 2 Taylor series. But it has denominators in here, and so if this step becomes too long, then this denominator kicks in and automatically divides this down. So this is a lot more stable, and this is what Gaussian uses today. This rational function optimization, it behaves better than Newton-Raphson or quasi-Newton, particularly in the vicinity of various nasty places like energy surface inflection points. And then various coefficients can be put into here, various scaling on the S matrix. This is done automatically. I will not go into great amount of detail in here, except that this is the default method in Gaussian at the moment. Okay, so what would the program do? It will take your initial geometry that you have specified. It will calculate the energy and the derivatives of that energy with respect to atom displacement. It will check if this derivative is already close to 0. And if this is a close to 0 vector, then we are converged. We are done. We have located some kind of stationary point. Minimum, maximum, saddle point, we don't yet know. If it is not converged, so if the gradient is significant, if we are doing basic gradient descent, we minimize along the gradient direction line. And we take the step and we check again, we update the geometry and check it. If we are doing BFGS or DFP or Newton, then we update the Hessian, we calculate the quadratic step, we update the geometry, and we recalculate the energy and the gradient, and so this loop goes on until the gradient is small enough. And gradient corresponds essentially to forces on atoms. So at the equilibrium geometry, there are no forces on any atoms because all the forces have compensated themselves. This is an equilibrium geometry. And so when the gradient becomes smaller than a certain threshold, which Gaussian sets automatically, it says, okay, I am done calculating. Now, there are various pitfalls in there. For example, if you are having a linear molecules like this pair of fused acetylenes, it will stay linear. It's genuinely a linear molecule, but of course in a linear molecule, dihedral angles are poorly defined. And so doing linear molecule optimization in internal or Z-matrix coordinates is a bad idea. It will blow up. So only for regular organic structures like this one is Z-matrix a good idea. So always think about, okay, what is my molecule looking like? Is it a good idea to use this or that particular coordinate system? If you are using internal coordinates of your own design, you have the option of running the singular value decomposition at every point to find out if any of your coordinates are linearly dependent. And if they are, it's a bad idea because linear dependence means that the Hessian is going to be singular, non-invertible, and then the optimization will fail. So there are various, they're not very common, these pitfalls, but with molecules like this, they do exist. And to give you an example of how long convergence takes, benzidine, so maybe a couple of dozen atoms. If you are using exact Hessian, so full Newton-Raphson in Cartesian coordinates, 125 iterations, in redundant internals, 110. If you are using exact initial Hessian and update it with LBFGS, 200 iterations versus 150. If your initial Hessian is approximate and is updated with LBFGS, 300 versus 200. And if you just straight use a unit matrix, then Cartesian coordinates simply fail, right? So it crashes after 768, and in redundant internals, you would still get there. So unfortunately, at this point, right, when you have to use thousands of iterations, energy minimization tends to be a dark art, which one needs to have plenty of experience with, and, well, your homework will hopefully supply a little bit of that experience. If everything else fails, you can always scan them explicitly by just manually incrementing a particular coordinate and seeing where the minimum roughly is, and then starting from some location close to that minimum and hoping for the best. But that's very uncommon because, of course, typically energy is a smooth function of atomic displacements, unless you're hitting some seriously eccentric ground states. Examples of this is from my research from the recently published papers in Kuprov group. This is difluoropropane used in some pharmaceutical research. And here, for example, we need to find out what energy minima does this have with respect to the rotation of this group and the rotation of that group. So we have this dihedral angle and that dihedral angle. And what we can literally do is instruct Gaussian to try every value of this and this angle, compute the energy, and plot us a surface. And this is how such surfaces look like. That's our first angle from 0 to 360. That's our second angle from 0 to 360. And that is the energy. you can see there is a huge maximum where these two fluorines collide, and they are strongly negatively charged, so repulsion, so the energy goes into a maximum. But there is the global minimum, and that is here, and that is a configuration where the charges are sufficiently far apart for the Coulomb interaction to be minimal, but also various covalent effects in here get themselves simultaneously into an energy minimum. And then if we calculate the probability of a molecule having a particular conformation, we have to take these energies and put them into the Boltzmann equation to get the probabilities. So there is this local minimum, and there is also, you can see behind this fountain, there is also a fairly deep trough in there. That's another large minimum. And so if we do the Boltzmann probability density at room temperature for this molecule, you will see that this combination of dihedrals and that combination of dihedrals dominates, but to some extent a few other conformations are also populated. This is called conformational analysis. And this is used in pharmacology because ideally you would like your molecule to have a specific conformation that binds the particular pharmaceutical target. The closer it is to the conformation that binds, the better. And a lot of pharmaceutical research is about putting various functional groups in the right places of the right molecules to make sure that it does what it's supposed to do. And in our case, we wanted particular J couplings. It's a parameter of nuclear spin interaction. I wouldn't bother you with what it is, but we can scan it as well as a function of the same angles. And then if we multiply this by this, we can see that this particular conformation makes the dominant contribution to the magnetic interactions in this molecule. That's another example. This is proline, a cyclic amino acid that is responsible for all sorts of sharp turns and corners in proteins, and it's also a common visitor in protein and peptide-based toxins. So if you ever get bitten by a snake, the snake will inject into you all sorts of nasty peptides. And significantly, those peptides contain a lot of prolines because they need to be, well, beastly in various ways. And then the question is, which of the many conformations that this molecule can have? So trans-endo, trans is with respect to the rotation of this group, and endo reflects which atom is bent inwards in this five-membered ring. Then cis-endo, cis-exo, trans-exo, there is an entire cogwheel of possible molecular conformations in this case, and we can scan the corresponding energies, and we can say, well, okay, this radial coordinate here is the magnitude of the twist and bend, and the angular coordinate is which atom is bent out of plane in this five-membered ring. And you can see we do have a single global minimum in this case, and that is the geometry that this molecule will predominantly adopt in some room temperature liquid. So the scans here are quite extensive. It's not very often that you need to do that, but you can see how you can get plenty of information on what kind of shapes your molecule can have, and in a lot of cases it means more than one. All right, that's me.